Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to introduce Sean Gao from CMU. Sean did many interesting things. He defined a notion of delta-decidability that's very interesting. Today he's going to talk a little bit about that, but he's also now working on cyber-physical systems, and I'm eager to learn more about it.
Thank you. I think it's okay if I just stand here? Or? Yeah. Okay. Hi. It's really an honor, a great honor to be here. I want to talk about our recent work on this emerging field called cyber-physical systems. A cyber-physical system is a combination of digital computation and the physical environment. Basically, what you have, I mean, this is actually part of every sophisticated machinery in our daily life. You have some kind of chip, you have some computation going on, and you have the computational part interacting with the environment. Right? It gets information from the sensors, and it has actuators that can control the physical environment. And all this are done in real time. Those systems are really everywhere. You can see that all the big sort of companies that are not considered as software companies, they're really what we could call cyber-physical systems, because they need to develop those big machines and also the software that's going on in those machines. And here are some examples, more concrete examples. One is this one is the autonomous car being developed at CMU. So it has a lot of sensors and has its own actuators that it is driving itself. And this is what you see in a cockpit in a plane. And this is a cardiac pacemaker that people will have, in their body. And this is the control room of a nuclear plant. Okay. So all those systems, they have this characterization that it's, computation combined with some really some really important physical environment, some physical control problem. So the two most important feature about this kind of systems, one is that it's very complicated, right? So if you want to reason about the system combined with the dynamics of the environment, it's really a complicated thing. And the second thing, the other thing, is that it's very safety critical, right? So if you think about having a blank screen on your desktop and laptop, the most you're losing is a day's work. But if you have a blank screen on the plane, which actually happens in the I think it's the Air France flight in 2009, which crashed, and I think 200 people died or something. Hundreds of people died, and that was because the sensors, the sensor for the speed of the plane was frozen, and the control software on the plane was giving a blank screen saying that you have invalid data, and it stopped to do anything. And then the pilot didn't know how to control the plane at that point, and it was just a few seconds, a window of a few seconds that they can make the right decision, but they made the wrong decision. They tried to pull the plane up, but that's the wrong thing to do, and the plane just crashed into the ocean. So the way that we look at it, we look at cyber-physical systems first from a model point of view. So you want to sort of understand the basic theoretical model for things first. That is something that we call a hybrid system, which is that you have different types of continuous control. Usually in control theory, you would talk about a continuous system, and you talk about just one set of dynamics. But in a hybrid system, because of the integration of digital computation, it's actually several sets of control rules, the continuous control, and between them you have discrete mode changes. If you look at it more mathematically, basically you have different modes. In each mode, you have a set of, say, differential equations defining the continuous thing. And then between the modes, you have decisions, right? If something happens, if the sensor value gets bigger than something, you go to that mode, and if something else happens, you go to another mode. So this is what we call a hybrid system. People would say that all those things are part of what we call embedded systems right now. And the reason that we talk about this new sort of field of cyber-physical systems is really you want to focus on the integration of computation, physics, and sometimes you have communications networks. Well, in the usual setting in embedded systems, the problems you are mainly dealing with is the limited computation resource that you have. But that's not that's still the important part of it, of the problem. But the key thing now is the integration of digital things and, let's say, analog things, right? Discrete things and continuous things. And it's really the hybrid picture that's important here. And the most difficult task is to cope with the complexity of those systems and ensure the ensure the reliability of those safety critical systems. So what we want to have, as people start to work in this field, we want to have a guiding roadmap, right? A methodology that you can understand, you can use to know the things that you want to do on those systems. And by that, it's usually several things that you want to have. First, you want to definitely have a language to talk about the things you have, right? You want to have a language to model those systems, and you want to have a language that you can specify the properties, the questions that you want to solve. And then you want to have a systematic theoretical understanding of what you can do, right? What you can solve. And that's the second thing. You want to know about at least the theoretical computability and complexity of the problems that you're facing for those kind of systems. And then you want to have a systematic way of dealing with those questions, right? Those methods that you propose in a systematic way, they should respect the complexity of the problems. And also, there should be evidence that you can have realistic tools that can help you to solve those problems using the methods. And then, in the end, you want to have a reasonable understanding about how you can go from theory, from theoretical models, from formal things, to actual systems, to a piece of C code in your plant, your nuclear control system. So this is the list of things that we would look for in coming up with a methodology, and there are a lot of difficulties with this, just because of the high complexity of the problem that we're looking at. So first, when people try to model cyber-physical systems, hybrid systems, we realize that I will come back to this later. Actually, it's going to be the first thing that I'll talk about. It's quite difficult to have a formal language to um, to contain all the features that you want to have to describe those systems. It's hard to put in, say, differential equations and logical decisions in the same framework. Of course, there are a lot of proposals, but we're going to say that we have a simple, not simple, but a first order, a sort of standard logic that can allow you to express all those things. But that's not a very easy thing to do. And then very early on in the proposal of hybrid systems, people realized that the almost trivial questions about hybrid systems are undecidable. For instance, reachability for hybrid systems with constant dynamics, really even simpler than that, having two or three variables that's having a dynamics of one. Just those very simple constant dynamics give you undecidable problems because you can encode Turing machine and do a lot of fancy things. So there's really a pessimistic outlook at the problems. It looks like nothing can be solved, right? And the tools, because of this, the tools that are proposed are usually focused on very simple problems. You don't target at say realistic systems with nonlinear differential equations and very complicated decision changes. That the tools are not available to handle those systems at all. And then there's a lot of research on hybrid system theory, and the transition from the theoretical results to the practical system is not very clear. So I'm going to talk about the language problem first. I'm going to talk about the logic that we're going to use. What we need, if we try to come up with a language, we need to have several things, right? So the first thing, we want to reason about systems that are in the Euclidean space. You want to talk about the real numbers, right? It's not, the digital controls anymore. And then you want to have your usual logical constructions. You want to have Boolean connectives, and you want to have quantifiers. And then you want to have all the real functions that are actually needed in the engineering of those systems, because the engineers are building those systems already, right? And they have good theories about good control theory, different things that they can reason about them, and they know partially how to build the systems. If you want to have a general methodology, at the minimum, you need to be able to talk about those functions, right? And that includes, polynomials, transcendental functions, differential equations, and everything else. That is very much beyond what I would say what we already have in formal methods. I mean, the logic that we have, temporal logic, different kinds of first-order series, they're really not containing those kind of actual real functions that we would like to have. This is why we first studied this first-order logic over the real numbers with what we call computable real functions. This concept comes from computable analysis. So you have a real function. The formal way of understanding a real function is really to look at it as a mapping from an infinite sequence approximating your argument of the function to an infinite sequence approximating the value of your function, right? So basically, what is a sine function? It's taking a sequence, a Cauchy sequence approximating x, and there should be something that's giving you this approximation to the value of sine, sine of x. And if you have such a machine, you would say that this function is computable. So all those functions that are computable in this sense, they're called type 2 computable functions. It's called type 2 because it's talking about functions on sequences of integers, which are like functionals of those functions, right? So it's type 2. And we don't need to go into the deep theory of computable analysis, but it's enough to know that almost every numerically computable function is computable in the type 2 sense. So you can have all those functions, trigonometric functions, exponential functions, differential equations, even ordinary or partial differential equations. As long as you have a reasonable procedure to compute the function numerically, we say it's very likely that you can prove that it's type 2 computable in theory, and it's part of this set of functions. So we talk about the first order series over the real numbers with arbitrary computable real functions. So it's LRF. R is a real number. You talk about things over the real numbers, and this F is the set of arbitrary computable real functions. So it includes all the functions that I just mentioned, and you can write down formulas like this, right? So you can say this is something that if you give it to an engineer, it will look like something that's saying you have two signals, and you're wondering if there's some coefficient such that they're not exponentially far away from each other. So this is the language that you can describe. I will later show you that's the case as well, that you can describe almost every problem in, let's say, control engineering or this kind of topics in continuous systems. But of course, the trouble is you can write down those functions, you can define this theory, you can throw in all those functions, but the formulas are naturally undecidable. It's just too complicated because even the simplest trigonometric functions combined with arithmetic is able to give you natural numbers, and that gives you an undecidable theory. But then we asked this question, those formulas are so difficult to handle from our perspective. Then why is it the case that people are solving engineering problems every day? Right? There's got to be a reason for the routine procedures that engineers can use to build those systems and to reason about those systems. And the key of the change of perspective is actually we need to look at numerical procedures. We need to have a way of logically, formally understanding numerical procedures that are used for handling those functions. And this is a notion that we defined. Suppose you have an LRF formula, a formula that contains all those computable functions and all. You can put it in a normal form like this. I'm not gonna. This is gonna be easy to see. You can push all the negations inside, and you can. All you need is to have these two kinds of relations, right? This is a normal form. And we define the delta weakening of that formula to be something that you only make minor change on the atomic formulas. You change the zeros, you relax them by minus delta. Okay? So you call this phi of minus delta, which is the delta weakening of the formula. You can also define delta strengthening of logic formulas by just use positive delta. But we don't need to talk about that here. We're going to mention that later. Then we define this notion called delta decision problem, which is instead of asking whether a sentence is true or false, you allow one-sided errors. Okay? So you say that your procedure can return one of the following answers. Either phi is false, or phi of minus delta, which is a relaxation, a weakening on the original formula, is true. Okay? So again, you can define that phi is true or phi plus delta is false, something like that. It's a dual of this. They're all called the delta decision problem. And the key theoretical result that's leading to a positive outlook of using using this language is what we call delta decidability over the reals, which is that the delta decision problem for any of those formulas, the assumption is that they're bounded, which means all the variables are bounded in bounded domains in the formula. All those formulas are delta decidable. This is in sharp contrast to the fact that very simple formulas of that kind, if you only have the trigonometric functions, they are highly undecidable. And actually, you can have a complexity matter on those sentences, which is that sigma n sentences just in the polynomial hierarchy raised by the complexity of the functions that you have. And the easy way of understanding this is that I could tell you the SMT problem, the existential formulas containing trigonometric functions and exponential functions, which are all polynomial time computable continuous functions in the type 2 sense. The complexity of solving those formulas, the existential formulas, is just NP complete. Okay, so that is, if you don't look at the delta decision problem, if you look at the standard decision problem, it's an undecidable problem. It's actually highly undecidable. But if you look at the delta problem, it's actually NP complete. It's actually not harder than the set solving problem itself. That is a very positive result for this, right? I mean, it's still NP complete, but it's really much easier than what we expected. And then we are done with the language. We can start talking about the models. So a hybrid system, I just showed some pictures, but a real definition is something like this. So you can have a set of formulas called the flow. They define the continuous dynamics for each location, each control mode. And you can have a set of formulas called the jump that defines the conditions for you to switch between the modes. And you have invariants, and the invariances are the conditions that says, if you want to stay in this mode, if you want to do the continuous flow in this mode, you have to satisfy some condition. And the initial conditions are the things that you use to start the system. Everything can be written in this LRF formulas because I just said you could have differential equations. The solutions of differential equations are computable. They're in the set of this F, and you can just write down all those dynamical system, continuous system that you're interested in. So if you look at this automaton, and if you look at the execution of those automaton, you're going to see something like this. The trajectory of hybrid automata are what we call hybrid trajectories. They're basically piecewise continuous, surfaces in the state space, because in each switch, I mean, in the disconnected points, it's the switch between different control modes that you're doing. And if you let it go through time, it's going to be like this. And on the left-hand side is the notion of hybrid time that's used in producing this picture, because you can now consider time to be a two-dimensional structure, where you keep track of the discrete changes you have, and you keep track of the time duration you have in each discrete location. And they have you can define a mapping from here to here, and that's the trajectories we're talking about. This is an example of a probably a most popular simple model of the hybrid system, which is a bouncing ball. Okay? So I didn't draw the ball here, but the idea is you start with some ball about the ground, and you drop it and make it do free falling. And you can have the first state to be going down, and when you hit the ground, which is that the height of the ball gets to 0, it's gonna bump up, right? And this two modes will alternate for many times. This is actually something we have in our tool that I'm gonna mention later. You can just write down those formulas just on in a simple text. And this is the trajectory that also we can produce it from our tool, but it's something we just saw. It's piecewise continuous, right? So this is like the ball is gonna bump back a few times, and the velocity changes based on the different modes that you have. And this is a more serious model. This is actually a faithful characterization of this atrial fibrillation problem. So you can consider the heart as a hybrid system, and you can make transitions between different modes. And in each mode, you have a set of quite complicated differential equations, nonlinear differential equations describing the behaviors. And this is the trajectory of the system that we can produce by our tool as well. So now we're done with the language and the models, and we can start talking about the questions we can solve. We want to solve about those systems. Usually, we know that given any system we have, the questions are mostly, of course, you can have very complicated problems, but the two big categories is safety questions and liveness questions. And in the context of hybrid systems, most likely you either talk about reachability, which is a safety property, or you talk about stability, which is more like a liveness property, because you're going to say that it's going to reach to some point such that the system stabilizes. The formula here is a bit complicated. It's not really in the language that I just defined, because you quantify over the trajectories, but I'm going to explain how you actually do them using the first order logic that we just defined. Okay, let's look at reachability first. The standard way, one of the standard ways of dealing with reachability questions is to use boundary model checking, right? So usually, when we talk about boundary model checking, we have in mind something like you have a finite state system, and you unwind the system up to some finite depths, and you solve the question of whether some unsafe property is satisfied. But we can do this just using the logic that we just talked about. You can you can unwind the discrete changes in the hybrid system, and in each change you have a continuous flow that's defined by the flow predicate of the system. So you basically start with the initial states, and you have a flow that's giving you something like this. You start with, let's say, x0. You start with x0, and you take some time, say t0, and go to another value. And that value satisfies the flow predicate, right? It's like a solution of your differential equation up to some time point. And then it's possible that you want to make a jump from, from the end of your continuous flow to a new set of states, and you switch mode. So basically, you want to encode the possible transition of the whole system using this logic formula. And then you say, after K unrolling, you have you ask the question of whether it can be an unsafe state. Right? So this is the first order encoding. And here I'm simplifying a lot of details. Actually, when you don't see anything about the mode invariant here, right? Because actually, if you have the invariance, you have to say something like, the invariance tells you that during the flow from xi to xit, you should stay in the invariant. So if you use the logic language to say that, it's like for all t within 0 to ti, the invariant should hold, right? So that's actually an exists for all sentence if you write everything down. And then if you have non-deterministic flow, it's even more difficult because your first order language cannot choose between different possible flows. You need to have, you can read it in the paper, that you need to have another existentially quantified set of variables saying that not only that you are always in the invariant, but you can actually follow all the possible points and they form a one particular trace in the continuous flow. That's something you can encode in using exists for all exists. So actually, given this encoding, you directly know that bounding model checking problem for those systems, for those systems, the complexity is actually, if you don't have invariance, it's just NP to the C, where C would be the complexity that you have for the functions in your system. And when you have invariance and non-deterministic flows, you will correspondingly have, sigma 2, sigma 3 problems. So you can easily obtain all those complexity results. Then the delta decision that we were talking about is a relaxation of the standard decision problem, right? So here you need to make sure that this relaxation is not doing any harm to you. And this is why it doesn't do any harm. Basically, if you use the delta decision procedures, you solve this formula, I omitted the existential quantifiers. I mean, all the quantifiers, all the variables should be existentially quantified. So if you solve that satisfiability problem, either you know that there's no solution, right? Or you know that there's a delta set solution, a delta set answer. So that corresponds to two different claims. Either you say that the system is safe up to the depths that you have unrolled, or the system is delta unsafe, which means that you have found a solution to the formula, which is you would say a bug falsifying the safety properties that you have, but it's delta set, which means that your actual system may not have this bug. That's possible because we may be wrong. We may be saying, we say delta set, it may be actually unset. But we know that given some perturbation, this weakening on the formula, this weakening on the system, this bug would actually be a bug, right? So, so if you think about it, delta, we just said, delta can be arbitrarily chosen, right? So if you're an engineer, you can choose a small enough delta such that this answer actually tells you about the robustness problem in your system. So that is why this relaxation is actually helping you with this analysis. Right? So with a delta perturbation, the system has a bug, which means that the system is likely going to be wrong in practice, in reality, if you have some kind of error going on. And if the delta is really small, you really should be worried. And then another way of doing reachability, another category of methods, is to use inductive invariance, right? So you want to show that the system satisfy some safety property because you can find a set such that the system basically never goes out of that set, and that set actually implies your safety property. So you're like doing an induction proof mathematically. So using the formulas, using the LRF formulas, this kind of technique can also be easily expressed. So basically the idea is that you have this formula encoding the invariant, and you just want to make sure that at first the system starts from that invariant, and the flow of the system doesn't bring you outside of the invariant, and the jump of the system doesn't bring you outside of the invariant as well. And then in the end, the invariant actually implies the safety property, right? So one difficulty in the standard approach to this is actually this flow part. So in discrete systems, we can say that you're in the invariant now, and in the next step, you should not go outside of the invariant. But in a continuous system, you don't have this notion of the next step, right? You don't have the next time point to talk about, and you don't know what to write. So there's a lot of research going on saying that, for instance, you can consider the essentially the vector space, right, and come up with something called the differential invariant, such that you can just look at the derivatives of the right-hand side part, the right-hand side of your differential equations, and make sure that they do not bring you outside of the invariant. But there are many tricky problems with that approach. Actually, I'm not gonna go into details there, but what I wanted to say is just using this logic that allows you to write down differential equations. Actually, you can now throw in a really small epsilon that is good for you modulo the delta decisions that the delta decision correctness guarantees that you're going to make. You can choose that epsilon such that you can directly write down this differential equation and ask, the next step is actually this epsilon step. So again, you can delta decide the formulas that you just listed here. Here, actually, what I omitted was the universally quantified variables, right? All the variables should be universally quantified, and you should ask a solver about whether the negation of that formula is satisfiable. And if that is not satisfiable, you would say true. You would say that the invariant actually holds. And if the formula is satisfiable, you have found a counterexample to the proof rules for the inductive invariant. And what you can claim using a delta decision procedure is that the invariant would fail under, again, delta perturbations. So this is how you could use the delta decisions to do unbounded reachability checking. And of course, the most difficult question is how you can actually search for those inductive invariants. And there are methods like template-based search where you leave out some parameters. And those questions can also be easily encoded because you just need one more alternation of quantifiers. And you can show theoretical results saying that the template-based search for invariance is like sigma 2 to the c, things like that. There are results that are easy to get. Now, the other type of properties that we usually worry about for hybrid systems is stability, right? But bounded time stability is really can be encoded just as reachability. And you can define notions like bounded delta stability, and you can, again, give complexity claims about that. That's why I call it a general methodology. It's really, you write down things in this logic formula, which gives you, for free, all those complexity results for those problems. And unbounded time stability is like, it's a bit like termination as for programs. It's something instead of the ranking function that you're looking for, you will look for Lyapunov functions. And you have conditions for the Lyapunov functions to work to guarantee the stability of the system. And all those you can describe by this logic. I just won't write those formulas anymore. So I just want to add in this part about our tool that can actually solve the formulas that I just wrote down in all those slides, right? It's available at dReal webpage. You can find it on my homepage, and if you just Google for dReal, I'm pretty sure you can find that. It's open source, and it can handle all those functions, all those formulas that I just mentioned. And for hybrid systems, we have a front end where you can actually put in the hybrid system descriptions that I just mentioned, and you can ask about reachability questions and different things. So the tool is actually quite scalable. I mean, we proved complexity results saying that it's not much harder than SAT. It's not much harder than this, NP-complete problems that you actually routinely can handle. We actually also see this in the performance of our solver. We have handled formulas generated from boundary model checking of some complicated systems that I probably show on the next slide that contains hundreds, actually, I forgot, 800, 900 of variables. And they involve, again, like 200, 300 nonlinear differential equations, and you can actually solve them. And there's no serious limitation on the signature that you can have in this tool, because basically, you could recall that our procedure are using those numerical algorithms, and as long as you can numerically compute something, you can put that as part of your decision procedure, and you can delta decide those formulas. So in the tool, we allow those trigonometric functions, differential equations, and all. So we try to handle models from many domains. We are working on car transmission and flight control, and we have results on biomedical devices and cancer therapy, and we're also doing power system, which contain a large number of differential equations with trigonometric functions on the right-hand side that are really, really big models. This is just to show you a few systems that we can handle, and I won't go into the details of them, but you can see that they're complicated differential equations, and these graphs are showing you the solutions. Basically, if you want to solve a reachability, if you want to answer a reachability question, we can give you a witness for a for the answer that your system can actually delta reach your goal. So those pictures, they're actually quite non-trivial. I mean, each line is actually obtained from a trace of, how long is it? Somehow do you remember? It's very big, so it can be like, can it go up to gigabyte? No, not yet, right? But it could. I mean, yeah. So it's actually quite non-trivial to produce those graphs. So now I'm gonna go more into the design or synthesis problems into those hybrid systems. And the reason that we can talk about them is because we realize that, I mean, not that we realize, but it's just everyone knows that it's just about solving the same type of formulas, but asking for more solutions for some different variables, right? All you need to do is to parameterize the dynamics that you have in the system. And you want to ask the question that, how do I design the system such that within a certain bounded time, you can reach a particular goal? And that is simply what you can write down with this logic formula, and you can just solve the decision problem of this, and you will get a list of solutions for those parameters. Here, notice, precisely speaking, when we talk about delta decisions, delta weakening, you're actually ensuring that your error is on the right side, right? On the the correct side. I mean, your error is actually helping you to debug the system. And if you want to solve the parameters, actually, you will need delta strengthening instead of delta weakening, because you don't want to say that this solution may work if you have some perturbation, right? You actually need to say that this solution should work if you, regardless any possible perturbations that you have. It's a dual of the problem. And actually, doing the delta strengthening is not an easy thing. So this is why synthesis problems in this domain is harder, at least harder practically, than the verification problems. It's just because to get the delta strengthening of formulas, to solve those, you need to have under approximations of the solution sets instead of the over approximation of solution sets, which are actually the assumption of all the current algorithms in this area. So the formulas the algorithm that we implement in our tool, they give over approximations. All the decision procedures are usually targeting at verification problems, which require you to give over approximations. And this whole direction of doing under approximations, when you solve the formulas, it's just starting. And this is something you need for synthesis problem. But for now, we do handle those problems, and we can do a simple design and verification loop, because you can sort of find a solution and then try to verify that it actually satisfies your property, so that you throw away the errors on the bad side. So you can do things like that for now, but in general, you would need a new set of solving strategy. And you can also do a lot of fancy things that are usually talked about in control theory. You can actually do optimal control. Here I'm just using a simple formulation of the thing. Basically, you want to reach some goal, and you also want to make sure that the cost of your control design is actually at the minimum. Okay? So usually, although here you have one more alternation of universal quantifiers, you're usually okay with replacing this by some goal that you want to have. So basically, you don't have to find the absolute minimum cost, the control plan that gives you the absolute minimum cost, but you are okay with finding a plan that's giving you a cost smaller than something, right? So you can usually approximate this universal quantification here. And then I'm not going to go into the detail of more things, but you can do them. It's just a matter of looking at the problem statement and encode them as logic formulas, and then understand the solvability, complexity, and actually having solvers that can actually solve them. And in general, you could think about a sort of algorithmic control theory. And this is probably a term that's used by others as well for maybe different meanings. But basically, you can think about encoding all those control problems into the appropriate logic formulation, and then you can use logic solvers like the ones that we just saw to solve those problems directly without any manual work, right? You could provide some heuristics that are built into the solver, but you provide this interface that the control engineer could just write down the question that they are asking, and you're just directly calling the decision procedure to solve the problems for them. This is really like lifting what people are doing in the linear dynamical systems to this nonlinear and hybrid domain, right? In linear systems, you usually would have a program running linear algebra, and there are very clever algorithms going on. But if you are beyond that scope, you basically have no systematic way of doing things. But now we're basically saying you can just write down those formulas in a formal way, in a logical way, and then use the automated reasoning tools, which are just extensions of the algorithm that you probably originally had, but they're now having logic capability for doing the logic decisions, which is the hybrid part of our system, and the capability of handling nonlinear differential equations, which is the nonlinear part of our thing. The whole the whole framework becomes this formulation first, and then solving next, and then you're done. So the hope is really to have scalable solvers that contains all the computational power you have in your usual standard algorithms, and put them in this logic framework that you can just use to solve those questions. And then at the end, I want to talk about this mapping from from theoretical models, from formal answers to the actual programs that you can actually have in those systems. The observation that started not just our work, but I'm sure everyone else's work as well, is that the embedded software, although they're very safety critical, they're very complicated, they're in this they have all those difficult continuous mathematics going on, but the program structure itself is actually pretty simple. If you just look at what you run, the software in a car, actually we have practical experience with some of that. You would see just a big loop, running at certain frequency, and within that loop, you would rarely see very advanced programming techniques, right? Most likely you don't even need pointers. You would never have recursive calls. You would never have complicated programs, constructs. And that, if you think about the problem in more detail, you see that it's really, I mean, the gap between the theoretical model and the actual code you have is really not that big. I mean, the gap is not that big. Basically, if you have a hybrid system that you can directly write down in any tool, you have the differential equations defined and you have the logical decisions, then the correspond, of course, this is a very simplified thing, but the basic idea is this, right? You have this big loop and you just have different cases and you switch between them, and each time you execute your program up to a delta t duration, right? So you're basically just translating the differential equations into difference equations that you have in the program. And all you actually need to do is to prove that the program that you have and the theoretical hybrid system model that you have, they are, they bisimilate each other up to some error bounds. And that error bound, of course, is related to the delta t that you pick the behavior of the function, say the Lipschitz constant of differential equations that you have, and some minor things. But the big structure is really something like this. So this is a simplistic picture of what people are now calling the model-based design idea, right? So you have formal methods, you have verification and synthesis on the model level, and then you would directly generate code from that model. And most likely, all you need is some mapping from the variables that you have in the theoretical model to the commands that you need in the program. And then you need to prove the faithfulness of this translation from the theoretical model to the programs. And that is a task that's much easier than the direct code verification that you can think about. Say you take this tens of thousands line of code from an embedded software, and you want to basically reverse engineer the original control design. That is a very difficult problem. But if you go from the model first, if you verify out your properties and then verify the translation is useful, is reliable up to certain error bound, you can actually do this, right? And actually, this is something that we are trying to do. It's a real small robot that we're currently building at CMU. The property that you want to ensure, so it's just a very small car. It's not even a car. It's two big wheels and one small one for balancing. And you want to program it so that it can run in any room, and it has sensors on it so that you want to verify that it never hits anything, right? It never hits a wall, a person walking by, it never hits anything. That's something that you can verify on the model level, right? And also to have that, you actually need to synthesize the controller. For instance, the small robot will see a wall, and it needs to reduce its speed, right? And it needs to reduce the velocity. And then what's the acceleration that you want to give for that? And that is something you can directly synthesize by solving the logical formulas describing the questions. And the model that we have, and not showing it here, but it's really just one-page hybrid automaton, just like 3 or 4 control modes, and each mode is really not very complicated differential equations. It's really a small thing that we have a student from mechanical engineering who doesn't really care about the logic theory or something. He just learns about this hybrid automaton language that we have, and he made this, and he's making this robot, and then we're going to just generate the code directly for the robot and see that the formal properties that we verify on the model can actually, you can actually witness that in practice. So this is roughly all I want to talk about. The message is that there is this promising framework based on the appropriate logic containing all those functions that you have in the Euclidean space and all. And you have automated reasoning underlying the logic. And the usual difficulty, either in theory or practice, can actually be avoided by our formulation of this delta problem, delta decision problem, or delta reachability. There are all the reasonable things to ask. And then this gives you a new set of techniques to handle nonlinear and hybrid system control. And the practical tools that we're developing, the power is going to keep growing, and we think it's very promising. And the future work is that you want to handle more complicated models. And also, now that you have the logic solver, you can actually basically translate all the sophisticated verification and synthesis techniques that you have in other domains, in hardware and software domains, to this field and improve the state of the art greatly. So that's all I want to say. Thank you.
You were talking about the undecidability results, right? For when you have samples.
Right.
But when you have, when the problem is bounded,
Right.
Do you have a reference for this?
Yes.
Because usually the standard proof is for the unbounded
Exactly.
space.
Exactly. I do. So that's. So I think it's actually open whether the sign function itself. So just adding this one single function gives you undecidability. I think that is still open. There are some constructions in the papers. And you can easily show that it's undecidable if you have more complicated computable functions. I have some papers that I can show you. And so my guess is actually for bounded problems, if you have the sign function itself, it doesn't give you undecidability. But for a bit more complicated functions, you would have undecidable problems.
Yeah. No, I was wondering about the sign, because the standard proof for any periodic function, right?
Exactly.
It's for the unbounded case, right? So, even with grants, we were discussing, trying to dig a reference, we couldn't find a reference.
Exactly.
Unbounded case.
Exactly. So, I remember seeing some very complicated construction about how I think it's mainly about how you can encode Turing machines using using the sign function itself, just using the sign function. And the construction is very complicated, I remember. Actually, I don't know if it's still in our current version of the paper, but I think we put that as a question, like open question. Like, is it possible that it's bounded and you don't have delta? You just the sign function itself gives you decide. Yeah, that. Yeah.
The other thing is when you synthesize the code, I thought the differential equations would not show up in the code. So I thought they were part of the environment.
Right, exactly.
But why did you have an X in the pseudo code?
Exactly. That's really. It's actually. I shouldn't write it that way. I was just simplifying things, just to show that you can do things. But yeah. So what you need is to put the. So actually, we have this. U, right? So the control is the U variable. That's the thing that you really want to encode.
Yes.
So here, right? So here, I'm not talking about this difference between the control and the plant. So I was simplifying. So usually you just have U, and it's some other differential equation that you put in a difference equation form. Yeah.
Because basically you'd have like a sensor reading
Exactly.
the X
Exactly.
and reacting to
Exactly. That's what we're doing for the small robot here. Actually, we would allow the user to clarify some variables to be the sensor variables, and we leave them out in the synthesis. I mean, in the code generation. And if we run a simulation of the thing, we can actually make a product of the control itself and the plant model, which itself is also another hybrid automaton that gives you sort of the signal. So for instance, if you have a map of the room, you can put that in terms of a hybrid system that give you different sensor data for a different time. So you can take the product of those two automatons and have this full thing running for a simulation. And then for code, all you need is the control part.
I see. But when you say it's verified, never hits anything, you're going to have a model of the environment, right?
Exactly.
But because, I mean, how precise is going to be this model? I mean, because you can have people running from the robots.
Exactly.
I mean, what you're going to consider in this?
Right.
In this
That's definitely related to the actual parameters you have in the vehicle. For instance, the velocity of the vehicle is a range.
Yes.
So your property will likely be that if you don't have an object approaching your vehicle with a velocity higher than something.
Okay, you're going to consider the environment
Exactly.
also has a velocity.
Exactly.
Okay.
So I mean, like relative to So the final formal claim would be anything that we can actually verify on the model, and that will contain those parameters.
I see.
Yeah. So it just have a big thing hitting on the robot. Of course, it can avoid that. So under some assumptions.
You had some modeling language, like this is the dReal language?
Is it the bouncing ball?
Yes.
Right. So this is the front end that we have.
For dReal.
For dReal or dReach, whatever we call. So basically, you write down this hybrid system thing, and we just want to follow this theoretical format. Just invariant is something, and the flow you can put differential equation, and the jump it's just it's just SMT format. So and we generate the SMT formulas from that, and so this is the front end for bounding model checking, and we're right now doing the invariant based reasoning right now, and that's actually would be a simpler script that you can write to generate the formula.
And dReach is in OCaml, right?
Yes. Right. It's a front end of the dReal. Yes.
Cool.
Yeah.
But dReach does more than just being a parser. For dReal, it has some.
There's no computation going on. It just translates this hybrid system to SMT2 and we feed it to dReal.
I see. But do you plan to have like some doing things like code of influence, all these things, doing model checking?
Mm-hmm.
Maybe we can do some abstraction or
definitely yes. I was mentioning that all the techniques that you have in hardware software verification, they should be built into this, and you can just scale up to more and more complicated models. So we just want to provide this starting point that people can add things into it, and and somehow made it open source. So
dReach is not open source?
it is open source.
Is it?
Yeah. So just anyone can write scripts that translate to the formulas and all.
Cool. Discussion upstairs.
But don't you need to stop doing the recording?
Shut down?
No, I think they know.
Okay.